It looks a bit like a goldfish swimming around a bowl.
It does, doesn't it? It's quite hypnotizing, I
It
think.
is.
You could stare at it for far too long, and we've all, I think, all of us have lost hundreds of hours just staring at visual PDE simulations.
Hello, and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas.
And I'm Marianne Freiberger. What was that about, Rachel? Why were you looking at goldfish?
Well, actually, I was talking to Ben Walker, and we were looking at one of the beautiful simulations created by this amazing tool, VisualPDE, that he's developed with some other mathematicians. And you can really quickly create these simulations, these visual simulations of these physical models that you can play with. You can sort of poke and prod them, and you can watch them. And the one we were watching, we'll hear more about in this podcast. But honestly, it was beautiful. They are really beautiful to look at, and it's amazing how quickly, even if you don't understand the underlying mathematics, you really quickly develop an intuition for what it is that what's going to happen in these systems that they're describing.
Yeah, so I've heard and I've seen VisualPDE, and the PDE in the name stands for partial differential equation. And partial differential equations are the kind of equations that underlie a lot of the mathematical descriptions of the real world, because they sort of capture how things change over time or space. And of course, change over time and space is what sort of characterizes most natural processes or processes that happen in the real world.
That's right. And we met Ben Walker, who's from University College London, along with his colleagues Adam Townsend and Andrew Krause from Durham University, through this network we've set up called Mathsci-comm, which is a network for people who communicate or have a stake in the communication of mathematical sciences research. I spoke to Ben and Adam and Andrew in October this year. Let's go back to the simulation that Ben and I were looking at.
So the whole point of this was we were seeing a talk actually at a conference that a colleague of ours, Ian Griffiths, was giving about some research that they'd done during the COVID-19 pandemic. And this, amongst other things, resulted in quite a nice mathematical model of airborne virus transmission, which here we're thinking about COVID-19, but it really could be many things. What was quite cool about this model particularly was it fit nicely in the box of things that VisualPDE might be able to do. And it was also a model that had real world impact. So this was used to inform part of government during the pandemic. So this was real cutting edge science that it looked like VisualPDE was able to capture. And what we managed to do, having worked with them and their colleagues for a little while, was bake a really faithful version of that model straight into VisualPDE. So it's really the same model that you'd see in the scientific paper we have running in your browser. So what you can probably see on your screen at the moment is a nice yellow dot inside a square. And what this is representing here is the simplest possible version of this model, which is a source of virus in the middle of a room. So the box that you're looking at is, imagine you're looking top down into a room that's completely closed off. And here is just someone in the center of the room who happens to be infectious. So actually, if you click in here, this was something that was really nice with VisualPDE, with everything being interactive. We can have someone click inside the domain and it simulates someone coughing, for instance, or maybe it's important to abstract a little bit away from the technical details of whatever bit of biology. And this is really a caricature rather than something that you'd use to predict something, at least in our case.
Yeah, I'm
So that's very
definitely sort
simple.
of pushing. As I click the screen, I can kind of make the blob spread out, but it's in a very dynamic way. It's obviously sort of it's like I'm interacting with it rather than just pressing.
Exactly. Yeah, and that's really what you are doing. As you're clicking, you're directly interacting with the solution of this partial differential equation. There's a pretty complicated system under the hood doing this simulation, but it means that for you, the user, it's just clicking and everything responds instantly. It really is solving based on what you input to this thing. And that was something that was really nice. We weren't aware of this having been possible before with PDEs.
So what was it like playing with the simulation, with a model like that?
Well, as the quote at the top of the podcast said, it's incredibly beautiful and somewhat like hypnotizing. It's very, you get really transfixed by it. So this particular one is part of what they call their visual stories, which are the introductions to the tool VisualPDE. You don't need any maths to interact with these, and it's really easy to use. It's the context and what is happening in the simulations is all explained in the text surrounding it, and you can just it's so simple to interact with them. So the example he's looking at, you've got this person, the idea that they're a virus, someone with a virus in the middle of a room, and you can sort of click it to make them cough, and then you can interact with them in as you'll see. You can interact with them by adding in wind effects and things like that. And although for someone like me who doesn't have a huge amount of expertise in the mathematics, or for anyone who doesn't have any expertise in the mathematics at all, you can interact with it. But it's also, as you've heard from Ben, it's incredibly useful for mathematicians as well in building their intuition for what happens from these equations. So we're just about to get to the part of the simulation that we started with, the goldfish from the top of the podcast. So here's Ben again.
But now this is a simulation where rather than just somebody being infectious in the middle of a room, they're actually wandering around the room doing circles. I like to think of this as maybe a waiter going around a restaurant at some particularly uniform pace. And here you can see that, rather than just a big yellow blob that's in the same place, it's doing this, I think it's quite pretty circling, right, of this thing. And you can still click to cough, by the way, and see how that interacts with the blob that's going around. And you can see it passing through and heading over.
It looks a bit like a goldfish swimming around a bowl.
It does, doesn't it? It's quite hypnotizing, I think. This is you could stare at it for far too long, and we've all, I think, all of us have lost hundreds of hours just staring at VisualPDE simulations. So the point of this model wasn't just to have something spinning around. The whole crux of this model was to see, well, what difference does airflow make? Because we were all asking this question, towards the end of lockdown periods, was when can I go back into a restaurant? When should places open? And should we turn on the air conditioner, for instance? So that's what this model is really meant to do.
Yeah, so this really reminds me of the kind of things we were thinking about and writing about at plus.maths.org during COVID, during the pandemic, because we went to quite a lot of talks and conferences where the airflow around the room was being considered, and the models seen as mathematical equations are quite complex, and you need to think your way into it. But if you could see that displayed on a screen, that would just make so much difference. That must be so useful.
Exactly. It gives you a real intuition for what's going on in the model. And because you can play with it you can directly play with the mathematical model, with these mathematical descriptions of these systems, such as this one of the way a virus is spread around a room, without actually having to interact with the math. So you can play with parameters. You can change the so for example, with this particular simulation, as we carry on through down the visual story that Ben and I were investigating when we were chatting, the next step is it introduces airflow again, as Ben was talking about. And so you still have this circling waiter, which, originally I described as like a goldfish circling a pond. But as you introduce airflow from side to side, it drags particles of the virus along with it. And you can play with how fast that airflow is and what direction it comes from. And you can still click to cough. And you can really interact with that science without having to get stuck into that partial differential equation. And anyone, including a policymaker, or a building designer, or someone considering, how they are going to consider the airflow in a restaurant, they can all interact with that model really simply just by playing with it on the screen. Here's Ben again.
So we still have this circling waiter, but now there's some airflow from side to side that's interacting with this, and it's dragging particles of virus along with it. And really, the main take home from this is really complicated, right? This is not something that I would have necessarily predicted, even as a self-proclaimed scientist. Perhaps I wouldn't have guessed that it would look like this.
And here's Andrew Krause talking about the power VisualPDE has to open up the maths and science to many different types of people.
There are sort of two lessons, two important things here. One of them is that visualization, particularly web-based visualizations, have gotten better and better over the years. And as scientists, we sometimes interact with this. We sometimes build very nice videos, very nice things, but interactivity is one of the levels above that, right? That it's not just a video, it's not just dynamic, but it's something that someone can say, well, what if this was a bit different? Or what if I changed the scenario a little bit, right? And there are some, there was in fact a COVID-19 website built that tried to get across how network effects work and how SIR dynamics spread, and you could do things like introduce infection or turn on and off quarantine and understand in a somewhat intuitive way how different policy measures matter without needing to go into a lot of the details. The other side of it, the caveat, is that, of course, these sort of visualizations are caricatures, as Ben said. They're fundamentally limited. But that's kind of an important lesson in all of applied mathematics and all of modeling, is that we're sort of balancing between what we can simulate, what we can capture, the level of detail of the process we're studying, and then in order to be able to present this in a way that someone can still see the big picture, they can get the insight of, okay, airflow is causing something to happen, or movement is causing this to happen. And there's a delicate sort of nuanced balance between this, and this happens often in mathematics with rigor and intuition. We have this sort of tension between the two. Allowing someone to peek into this, to sort of say, well, I want it to be more realistic, let me add some features, let me add some effects, or I just want the simplest possible thing that shows the phenomena. This is, I think, something that researchers are very aware of, but often students are not, and definitely the public doesn't have as much intuition.
Yeah, so this is really interesting. It reminds me of a sort of ongoing work that we're doing at the moment with some researchers who need to communicate mathematical modeling, for example, to policymakers. And one of the lessons that came out of these kind of discussions is that it's really helpful if you can let somebody interact with your mathematical model.
Yeah, that's right.
And explore it.
Yeah.
And explore it by themselves, so that it's not they're staring at an equation that they don't understand, but they can actually play with it. So this seems to make this possible. And of course, the thing is that while for a mathematician, it might actually be relatively easy to write down the partial differential equation that describes the process and to write down the model, it can be very, very hard to solve that model. So,
and indeed,
what do we
isn't one of the big open problems in maths is solving a particular type of PDE called the Navier-Stokes equation? There's no general solution to that. We can only solve it in certain settings, sort of with a pen and paper, and then the rest of the time you have to run mathematical simulations of it. You have to run it through a computer to see how you start with your initial setup for your system, and then you apply these equations, these partial differential equations describing how things will change, and run it forward over time. And that's sort of this, we can't always solve them, but we can often, thanks to computers now, simulate what might happen. And here's Adam Townsend to explain more.
It might not be obvious why simulation is so important. I think typically, again, when you're teaching it and when you're learning about these things at university, you look at problems that you can write down and then you can solve them with pen and paper. But for a lot of physical scenarios or biological models, writing down the equations isn't that hard. Like broadly, you're trying to describe some physical system or some system where maybe two populations interact or two chemicals interact in some way. And writing down like the broad physics or the broad behavior of that system as an equation is not too hard. The problem is that once you've got the equation, then where are you going to go, right? There are very, very few equations that, particularly these partial differential equations, where you can just write down the answer or solve them yourself. So to be able to obviously understand these solutions, you really do have to simulate them, and that is pretty much our only way into understanding the systems or the models that we're putting together. And so that's why we spend so much time doing simulations. And it is important that we know that the simulations are correct, right? So there is time spent making sure that we've dotted the I's, crossed the T's. VisualPDE does a little bit less of that to be able to give you speed, but yeah, I thought it was worth adding that. I don't think it's obvious that most of the time writing down the problem is the easy part. Solving it is then hard, even for us.
And Andrew, Ben mentioned that some of the things that have resulted from the Visual PDE software, he didn't expect as a someone who knows the maths and science behind it. Have you had anything where you felt like you've got a new insight into something through your work on Visual PDE?
So indeed, we've now written actually a research paper, and we have a few more where the basic phenomena might have been known somewhere in the literature, or someone might have done a simulation, but because it's so easy to play and it's so easy, as was said, to spend hundreds of hours wasting time, we occasionally discover something and we said, oh, that's actually potentially not as well known as I thought. So maybe we should go and write a scientific paper. So we've now done this in one example by something that was in some sense discovered on just playing around. So the website is not as sophisticated as writing a high performance computing code. It has some limitations compared to very rigorous scientific computing, but it makes up for that in being able to rapidly interact with many, many parameters and to really play and explore. And it's fairly easy to find things that way. So we found several examples, I think, of things that we didn't expect, things that maybe there was some intuition that this might be possible, but actually being able to see it and play with it and build examples that have some behavior is kind of nice.
Have you got some sense of how other people, have you got evidence of other people using it, or some interesting ideas about interesting ways other people have been using the software?
A lot of it is replacing a bit what would either not be done because it would take too much effort, or again, this ability to play. So for example, there was a paper recently on a model of viral therapy for infections. And in this model, the researchers studied it in a sort of simplified mathematical one-dimensional setting, and they found some behavior. But of course, the really interesting stuff happens if you consider a population distributed in 2 dimensions. And you could build a simulation to do that. It just takes more time and effort and more coding. And as I understand it from chatting with the professor who was on the paper, the student had an interest in doing this, but they were near the end of their PhD. They didn't really have time to build a code. And so they just used our website and they just typed in their model, and they found all kinds of interesting things like waves of infection and spirals and complex dynamic behavior. I would say this isn't, in some sense, the fundamental story of the work they did, but it's a really nice addition, and it's a really nice thing for them to say, well, there's also all of this other complex behavior that you can see if you relax some of the assumptions, right? Sort of mathematicians often study really idealized objects. You imagine an infection spreading in a line of people, right? And they can't move out of the line. That's quite an idealized situation. And to know that if you have people spread in a room, or you have a population distributed over some area, that the dynamics can be really radically different, it's a nice thing to know, and it's a nice thing to be able to see and play with.
And here's Ben with another example of a surprising way of using Visual PDE.
Adam. I have one further example of maybe something which I didn't expect, which it was me using it, but I didn't think I would use it like this. It was an event where some industrial partners at my previous university were presenting some problems that should be solved, that what they wanted to be solved. This was like a workshop environment, a week-long event as part of the Samba CDT, which was really a really nice feature. And what was really surprising is that the students and people working on a potential solution to one of these problems wrote down a partial differential equation as part of a first solution. And then what they did was opened up VisualPDE and typed it in, and were able to show the industrial partner the solution of this PDE within about 5 minutes of them coming up with the model and being able to tweak things. And just seeing more things like that happen sounds really exciting. The way that we can, Andrew mentioned it in the context of, say, other biological researchers, for instance, but if interacting with diverse communities that might be industry or government, or just being able to prototype things and tweak and play and explore in that setting was something I hadn't expected. And it was really lovely to see.
So this sounds like a really powerful tool for communicating mathematical models to people who aren't experts. It reminds me of when Ben actually gave a short presentation about VisualPDE at one of the meetings of our Mathsci-comm network. And he presented a simulation that was showing how flooding would spread in a particular area of a town. And there is such a power, the visualization is so powerful to see where the danger spots are when it comes to flooding, and much, much easier to get your head around than reading a scientific paper or trying to get your head around the equation. So it's really, really useful.
Not only is it powerful and useful, incredibly useful for non-experts, it's also, as Adam's going to tell us, it's incredibly useful for mathematical scientists too.
What's really nice about that is that the way that you would solve this PDE or show the solution to this PDE before VisualPDE sort of existed is by programming it up yourself mostly, and that's really slow and it requires a lot of technical knowledge. We've sort of touched on this already, but the difference in time between here's the PDE, type it in, this is basically what it does, versus having to figure out, choose your favorite coding language, write it up in this, set up the sort of the domain, the area that you're solving the problem in, get all the boundary conditions in properly. That you have to understand the technicalities of how you solve these problems using a computer.
So this is an interesting example as well of how mathematics changes as new technology becomes available.
Yeah, that's right. And Andrew's just about to tell us about how VisualPDE and other tools like VisualPDE might actually impact maths research itself. Here's Andrew again.
I guess one final thing I might comment on, sort of generalizing this, is that there are a number of mathematicians at the moment who are looking at the use of computers. So mathematics has been a relatively slow subject to adopt computers into our daily use, relatively speaking. It happens much more on the applied side. But our colleagues, many of them who teach more abstract mathematical topics, they will sometimes use tools like Desmos or GeoGebra, but often these aren't complicated enough. Often they don't solve the university level mathematics, and they don't appreciate as much the sort of interactive side because it's in some sense not as popular in these areas. So people like Terence Tao and Kevin Buzzard and others have been developing ways and trying to convince, say, more theoretical mathematicians to take computers seriously, in a sense. And we're hopeful to a degree that we see more things like VisualPDE for other areas of what you might call advanced mathematics, right? So we think this is a nice thing. We're very proud of it. We're very happy about it. But I'm actually quite excited to see people do similar things for other areas of maths, because I think it has the opportunity to change, of course, how we teach, of course, how we communicate, but to a degree, how we think of these objects, right? Again, people 70 or 80 years were not thinking of these equations in the ways that we do. They were not thinking that you could just vary parameters and you could just move and play and interact. And I think it fundamentally changes our conception of the abstract structures. And it would be really cool to see this in other areas of maths, to sort of really take advantage of these modern tools that we have.
So these aren't just tools to help you communicate with researchers or industry partners or non-experts from outside maths. These are actually tools that could be really important in how both we teach, but even develop maths ourselves.
And I think this has been true for about 30 years for the people working in scientific computing, for the people who are writing, for those of us who do know the coding and the programming, this is how we've been thinking a bit more about these objects compared to people many more years ago, because we do tons of simulations, right? My sort of expertise coming out of my PhD was having done thousands of simulations and sort of knowing, therefore, how these systems behave away from, parameter sets where you could do pen and paper work, and sort of connecting the pen and paper work to things that you would see via simulation is harder, and it takes a lot of looking at lots and lots of pictures. And so a lot of what we've been hoping to do is to make this process easier, so that someone doesn't need to do a PhD where they spend a lot of time writing code and building something just to get this intuition. They can, in principle, get this intuition over a much shorter period of time, and then spend more time thinking of how does this jive with everything else I know, and how does this connect with other areas.
So I can imagine how this opens up new opportunities and new avenues for communication. And clearly, those guys you talk to are all very interested in communicating with different audiences.
Yeah, that's right. And when I asked them about their motivation for starting the project and being involved with the project, that was definitely part of it. And here's Adam again to tell us more.
But this was a nice project because it has combined this sort of nice mathematics with exposition, which is fun. So I spend a relatively large amount of time doing sort of maths outreach stuff. I help run a magazine called Chalk Dust. We're your rivals. It's fine. Okay. Happy to be here.
Friends rather than rivals.
Yeah. Sorry. Friends. New issue out soon. So it's nice to be able to do some outreach or some exposition from that, and then some of the sort of web tech stuff. Although Ben will tell you much more because he does a lot more, or he's done a lot more of the programming than I have. That's sort of just like a fun thing I've always been interested in. It's been a nice way to combine hobbies, taking those skills from creating GeoCities websites when I was 14 or something, and trying to convert that into something that looks pretty now that people will use. So it's been nice combination of hobbies.
Oh yeah, I like Chalk Dust. It is quite similar to what we do here at plus.maths.org. It's a magazine for the mathematically curious. And it comes out twice a year, I think, in print, but it's also available online. And we put a link in the show notes.
Yeah, there's lots of great stories there. And it's clear that for Adam and for Ben and Andrew, collaborating together as a group has also been a real motivation for the project, a real bonus of doing the project together. Here's Ben talking about his experience of working together on VisualPDE.
So it's really been I think it's fair to say it's been a passion project for the three of us to push this forwards. It's been a really nice thing to do in your spare time that brings together, I always liked coding and tinkering around with stuff, but I wouldn't claim to be particularly good at it. It's just being persistent and knowing the right people to ask the questions to, and really just try and get feedback and make it something nice. It's been a great fun working on it as well. I intend to keep doing that forever, basically.
This has been a really fun project. It is always great when you collaborate with people who are brilliant, and both Ben and Andrew are brilliant. And it's been really nice to join in on that.
That was Adam Townsend, and thanks to him and to Benjamin Walker and Andrew Krause for talking to us about their brilliant project VisualPDE.
You can find VisualPDE, and most importantly, you can play with it at visualpde.com. There's loads there to explore. That's it for this episode of Maths on the Move, the podcast from plus.maths.org. If you've enjoyed this podcast, please do consider recommending us to a friend, or you can rate and review us in the app you're listening to this podcast to. Thanks for listening, and bye for now.
Bye.